Rao Patro, Associate Professor from the Department of CSC, IARE. So today we'll discuss about one more important topic, that is heap sort. How sorting are useful in our day-to-day life also we can discuss. Generally, whenever you want to arrange the data, either in ascending order or descending order, that time you can use the sorting. So you can use heap sort to arrange the data either in ascending order or descending order. Heap is a special data structure which organize the data in a complete binary form. So whenever I say heap, that heap may be a min heap or max heap. So that means I can say there are two types of heap. One is min heap, second one is max heap. Max heap means it is also one type of complete binary in which the value in each internal node is greater than or equal to the value in the children of that node. So that means here you can see small tree here. The tree having set of nodes. Here this 95 is one of the node, root node, or also called internal node. Similarly 85 also one internal node. 45 also one of the internal node. 75 is also one of the internal node. So for every internal node we will have some children. So this internal node, or also called parent node, if it is greater than or equal to its both of side, then that type of heap is called max heap. So I can say max heap is a complete binary in which the value in each internal node is greater than or equal to the value in their children. Okay. Or in a simple short form you can say parent node is always greater than both the children node. This is a simple form. Okay, fine. Mapping the elements of a heap into an array is a trivial. If a node is stored in an index at k, then the left child will be stored at 2k plus 1 and the right child will be stored at 2k plus 2. Remember, if k is the index of parent node, then its left child will be available at 2k plus 1 and the right child will be available at 2k plus 2, because the heap can be mapped to a array. So my k is what? Index of the parent node. If k is the index of the parent node, then 2k plus 1 will be the index of left child and 2k plus 2 is the index of right child, provided the starting index of the array will assume that 1. In that case it is suitable. Similarly min heap. Min heap is also complete binary in which the value in each internal node is less than or equal to the value in the children of that node. Or in a simple form we can say the parent node data is always smaller than both the child. If parent is smaller than both the child, then that type of heap is called min heap. And remember, here also the mapping the elements of heap into an array is a trivial. If a node is stored at index k, the left child will be available at 2k plus 1 and right child will be available at 2k plus 2. These are the index of left and right child. So this is the general representation. Please observe here, this is a min heap, because here 15 is what? My parent node, which is smaller than both sides. Similarly, if you think about this tree, 45 is the parent node, smaller than both the child. Similarly here, 25 is the parent node, smaller than both the child. Similarly 55 is the parent node, which is smaller than both the child. So whenever this type of property is followed, then this is called min heap. Fine. Now think about this array. You can map this heap into a array. The elements of the array can be thought of as lying in a tree structure. A heap tree represented using a single array looks like this. You can assume that array is a contiguous elements. Now this complete binary is stored in an array. Please observe here, 65 is available at 1th place, 45 is available at 2nd place, 60 available at 3rd place, 40 available at 4th place, 25 available at 5th place, 50 available at 6th place, and 55 available at 7th place, and 30 available at 8th place. So that means this is your diagrammatic representation. The tree, same tree you can represent with a programmatic representation, that is using array. So that means a heap tree can be also mapped to a tree, a array. So this is available at 1th place, this is available at 2nd place, this is available at 3rd place. Similarly, this is available at 4th place and 25th available at 5th place. Similarly, 50 is available at 6th place and 55 available at 7th place and 30 is available at 8th place of the array. So that means you can store the complete tree in an array. So this is the general representation of the heap. So whenever I say heap, you can imagine just like one type of array also. So while storing array, it will store in a order. So heap is one type of complete binary tree. So using heap, you can sort the data. So whenever you want to do heap sort, first of all you have to create a heap first, then you can do start sorting. So a heap sort algorithm works by first organizing the data to be sorted into a special type of binary tree is called heap, or you can say it is one type of a complete binary tree. Any kind of data that can be sorted either in ascending order or descending order using a heap tree. And you can see the following steps to follow the heap sort. First, to create a heap sort, what you have to do? First, build a heap tree. First of all, you have to create a heap tree with the given set of data. Whatever the data is given, using the data, first create a heap. Second, after creating heap, remove the topmost or the largest element of the heap and replace it with the last element of the heap. So that means once heap is created, which heap? Max heap. Once the max heap is created, the topmost element or the largest element will be available at top of the tree. That is nothing but in the 0th position of the array. So once that element is removed, that can be replaced with the last element of the heap. So that means that element is over. Then after removing the element, you are replacing with the last element. Then second step, reheapify the complete binary tree. Again reheap, because after replacing the last element, again reheap. Third one, place the deleted node at the output. So that means this is in an order. So you are putting the maximum element at the output. Now this process will continue until the heap is empty. This is a simple algorithm for heap sort. Now you can see how heapify process works, because in heap sort the heapify is the main. So you are passing the array and you are passing the n and you are passing the n, means array is the list of data, n is the number of element and I is the element which one I want to heapify. Now I know my index of the element. I am passing the I, largest equal to I, and after knowing I, you can find, because I is what? The element of the root. After knowing the root, you can find the left index as well as right index. Left as well as right. So L will be 2 into I plus 1 and R will be 2 into I plus 2. If left is less than N and array of I is less than array of L, then largest is equal to L, because you would find which is the smallest one. Sorry, which is the largest element you would find. If R is less than N and array of largest is less than still array of I, then largest equal to R. So here you are finding out which is the largest element, whether left child is largest or right child is largest. Whichever is largest, you have to swap. So if largest is I, if the parent itself is biggest one, no need to swap. If parent index and ith index both are different, not equal, then ith index and largest index will be swapping. This is the logic for swap. Okay, then heapify again the process. So this process will continue until the complete tree is again heap, proper heap. So in a heap sort, first I am passing the array. After passing array, I am finding the length. Then after finding the length means the number of elements. Here my for loop starts for I in range of n by 2 to up to 1, because I am coming from the reverse order. So I am going to the last subtree, because from that onwards I have to do heap. So go to hub and come in the reverse order, then call the heapify process because you have to heap the complete tree. So this will create a maximum heap. After construction of the maximum heap, then here what I am doing, the last element and the beginning element, the zeroth element, I will swap it. So that the last element will be coming to the root. Then again heapify the process. Heap the process. Root element will be heapified. So this process will continue for all the elements. After continuing this, then it is printing the sorted data. So this is the way this heap sort program works. And the time complexity, each n insertion operation takes order of log k, where k is the number of elements in the heap at a time. Likewise, each n time of remove operations also run in the time order of log k times. So totally order of n log n time, because every heap is one type of tree. So the tree organization takes log n time, and n time it is doing that operation. So order of n log n time. So the time complexity in the all the three cases, best case, average case, as the worst case, will find same complexity. Most of the time they'll ask what is the time complexity of heap sort. So you should say it is n log n time. You can observe here how heap is constructed. Please observe here. I am having the set of data 40, 80, 35, 90, 45, 50, 70. Now this data you have to sort it by constructing a heap. Please observe here 40, 80, 30, 55, 90, 45, 50, 70. This is the a binary tree, complete binary tree. So whatever the data is given, I kept a simple binary tree, complete binary tree. After that, what you have to do? Here you have to go to the last subtree, because I told you n by 2. So in the previous program you have seen, I have gone up to n by 2. So my last subtree is 70, this one. Because here, please observe here, in the last subtree, 35 is there as a parent, but 35 is not the maximum, because here my goal is create a max heap. So I will compare both my child, left and right. Whichever is maximum, I have to take to the parent. So here 70 is bigger, so 70 will go in here. So 70 and 35 are replaced, means swap each other. After swapping, I got this thing. After this, then I have to come to this portion also. This is the right subtree. So please observe here, in the right subtree what I am doing, my parent is 80 here and left child is 90, right child is 45. So which is bigger here? 90 is bigger. So this 90 and 80 I have to swap. So these two I have to swap. After swapping, I got this. So observe here, I am going from here and then here. After coming here, then I have to go to my parent. First left subtree is over, right subtree is over. Then I have to compare with the parent. Now 40, 90, 70. 40 is parent, 90 is left child, right, and 70 is right child. So now if you compare these three, which one is bigger? Here 90 is bigger. So I have to swap 90 with 40. So after swapping, I got this. Okay. So after that, now my tree is ready. So 90, now 80 as 90 has come down. After coming down again, I have to check. Here 80 will be bigger one. Then if you compare both the child, my left child is 80, right child is 45, because 90 has gone up, 40 has come down. When it is come down, my 40 is parent now. Now in max heap, 40 cannot be parent. So I have to swap these two. After swapping, I got 80. So this is the final, my max heap. So this is the way the max heap is created. So now always you have to observe one thing. If max heap is created completely, then the maximum element will be at the root. So here the 90 is the root element. So that means the root will be always highest value. Now this element you have to remove. After removing this element, what you have to do? The last element of the heap, which is the last element? 35. So the 35 has to replace at the root. Now you can observe here. Yeah, 35 has come down. 35 has come to root. And the 90 is replaced here. So 90 has come to this place. Now again reheapify the process. 35 is the parent. 80 and 70 are the two child. If you compare, 80 is the bigger one. So 80 has gone up and 35 has come down. Again after coming here, 35 has come down. If you compare 35 with this child, 40 and 45, 40 and 45. So here 45 is bigger. 45 is bigger because in max heap, parent will be always bigger. So 45 has gone up and 35 has come down. So this is the final. So that means my heap is now ready. So 80, 45, 70, 40, 35, 50, 90. So this is the max heap. Now what you have to do? Once heap is ready, always once heap is ready, what you have to do? The goal is remove this root element and replace with the last element. Now this dotted line indicates what? This node is deleted. This means work is over. Now I am putting the 50 here. Replace. So 50 has come to the root. Now compare 50 with this both the child, 45 and 70. Now if you compare 45 and 70 with the root, because my root is 50, now which is bigger? 70 is bigger. So these two you have to swap. These two you have to swap. So after swapping, I got 70 and 50. Now 50 has come down this right side. Now you compare with this tree. Now here there is no more tree, stop it. So finally I got 70, 45, 50, 45. So up to this is already deleted node, means this work is over. So now I need to do interchange. Already dotted line is given. So this is the now max heap. So now here which is the root now? 70 is the root. And which is the last element of the heap now? The last element is 35. Now this 35 has to replace with 70. 70 will come down here. So that means the 70 will be deleted. 35 will be going to the root. Yeah. So 70 has come to. Now these three nodes are over. Now 35 has gone up. Now compare with both the child. 45 and 50. Now 50 is bigger than 35. So interchange these two. After interchanging, 35 come down, 50 has gone up. Again once 35 comes, now 35 having no more child. Stop it. So this is the final heap. So 50, 45, 35 is. Now it is a max heap. Once max heap is over, again 50 is the root that you would remove and put with the last element. Which is the last element here? 40 is the last element. This 40 you would replace with 50. So after replacing, 50 will come down. And 40 has gone up. Once 40 comes to top, compare with both the child. 45 and 35. Whichever is bigger. Now 45 is bigger. Interchange with these two. After interchanging, I will get 40 here, 45 here. Then compare 40 with both the child. But here no more child. So stop it. So this is the process. Now 45 has come up. Now 45 is the root. Now this one replaced with the last child. Which is the last child? The last child is 35. So this one you have to replace. So replace with this. So 35 has gone up. Now compare with 40. Now if you compare 35 and 40, 40 is bigger. So interchange this. So after that my 40 has gone up. Now parent is a bigger one. Now max is ready. Now delete this one. So put in the last place. 35 has gone up. Now there is no more node. Now heap is empty. Stop it. So this is the final heap. Means the final sorted array. So if you think about this final array, this will be 35 because this is the first place, this is the second place, this is the third place. That means 40 and then 45 and this is the fourth place, 50 and this is the fifth place, 70 and this is the sixth place, 80 and this is the seventh place, 90. So that means in the sorted array, you will find this type of data. So this is the diagrammatic representation, but internally the data will be organized in this way in the array. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.